So when last we left off, we had the distance from a graph to a single point. We are going to jump now to 3.5. And 3.5 is all about applications to business. So for those of y'all who the other week, the noise with the sound was off, first, can you hear me?
Yes.
Awesome. Second, to answer some of your questions about when are we going to use this, because that got recorded. What we're going to see here are a couple applications to when we're going to use this stuff, when it shows up in business. To start off with, let's imagine we have this company, right? And we want to maximize revenue. We know that the function for revenue for this company is going to be negative x cubed plus 450x squared plus 52,500x. And what this is going to represent, like I said, is revenue as a function of the number of units produced. What we want to know is what level, what x will produce the highest number or the highest amount of revenue. Right, we want to maximize revenue. So what we're looking for is going to be a critical number, right? First thing we should note is that according to this function, just because of what it's modeling, x has to be 0 or greater, right? Because you can't have negative output. So we know that our revenue is equal to, as a function of x, is equal to negative x cubed plus 450x squared plus stupidly large number, 52,500 x. And we know that x has to be greater than or equal to 0. Really quick, I'm going to jump to the next slide to the graph of this. What we're going to be looking for is the x that produces the maximum revenue. So we're going to be looking for this value 350. The way we're going to find it, we're going to start by taking the derivative of our revenue function. And then we're going to find the critical numbers. So p dx of our revenue function is going to be equal to negative 3x squared plus 900x plus 52,500. Now the first thing we can notice is that 3 can be divided out of all of these values. And the way we know that is that the digits in each of these coefficients add up to something divisible by 3. Pro tip, anytime you want to divide something by 3, and you have a random number given to you, if the digits of that number add up to a multiple of 3, that number is divisible by 3. So we've got 12, 9, and 3. So factoring out, let's factor out a negative 3 here. We're going to have x squared plus 300x plus 52 divided by 3, 1. That becomes 22. That becomes 15. And this should be negative and negative. Right? obvious factor is jumping out at me here. So we're going to have to apply, we're going to have to apply sorry, I'm trying to do this factoring in my head and it's not working right now. Yeah, we're going to have to apply one of our other tools, right? But because I have the answer on the next page, I'm going to skip to the next page where they factored it out for us. This will factor out to be -3 times x plus, or my mistake, minus 350. That quantity times x plus 50. Setting our derivative now to 0, we're going to get that x is either equal to 350 or to -50, right? So from here, we know that the only critical number we have which fits this interval is going to be 350, but we don't know if it's a max or a min just yet. So we're going to have to use some form of our first derivative test. So just for the sake of making this quick, let's apply 0 to both sides. I mean, let's set x equal to 0. We get -3 times 50. My mistake, -3 times -350 times 50. So we're increasing. And if we apply 400, we get -3 times 50 times 450, which is going to be negative. So what we found my mistake, greater than, sorry, and less than 0. So what we found is that we're increasing before we get to 350 and we're decreasing after it. So it must be that 350 is a max. So we know 350 items of production, 350 units, will maximize our revenue here. Does that make sense? Yep. Awesome. So jumping to the next problem then. This next problem is going to require some work. This next problem wants us to find out something about the average cost per unit, but it only gives us the cost function. So we have the cost function, cost as a function of x, where x is going to be the units of a product. It's going to be 800. Plus 0.04x plus 0.0002x squared. Well, the thing we need to notice is that this is the cost for some bulk production, right? If we put in X number of, or if we produce X number of items, this is going to be the cost. But what we want is something to do with the average cost per unit. So we're going to have to divide this by the number of units we produced. So our average cost function is going to be our cost function divided by the number of units we produced, which is going to give us 800 divided by X plus 0.04 plus 0.0002X. Now, observation here. We're producing things, right? So X is going to have to be 0 or greater. Agreed? Well, wait a minute. We've got an X and a denominator here. So X can't be 0, right? So we know X has to be greater than 0. Make sense? Now, we're going to apply the derivative. Which is going to give us negative 800 divided by X squared plus 0.0002. We want to minimize this, so we're going to set it equal to 0. It's going to tell us that negative 800 divided by X squared plus 0.0002 is equal to 0. We can subtract, or rather add, 800 divided by X squared to both sides. Divide both, or rather multiply both sides by X squared, and then divide both sides by 0.002. Which is going to give us X squared is equal to 800 divided by 0.0002. Now I don't know what 800 divided by 0.0002 is. So I'm going to jump down to here and zoom in to X squared is equal to a stupidly large number. I had to say that forcefully with that, stupidly. So X squared is equal to 4, 0, 0.00000, right? Now, to find the answer to this, to solve for x, we're going to have to take the square root of both sides. We're going to get that x is equal to plus or minus the square root of this, yeah? Which is going to come out to be a giant number. Or more specifically, just 2,000, plus or minus. Okay. So from here, we're going to apply our first derivative test again to find if 2,000 maximizes or minimizes our function. Make sense? Since we know x is greater than 0, we just need to know if 2,000 maximizes or minimizes. In our case, it's going to minimize. Which we can see when we look at the graph here. But notice if we were to look just at the graph, we couldn't pick out that value, right? And this thing is flattened up through this region, so it would be hard to be like, okay, which one exactly is the minimum? Folks at home, does this make sense so far?
Yes.
Yeah, awesome. So jumping to the next example, it's more of the same, except here we're given all the information. We have to build up the function from the very beginning, right? So if a business sells 2,000 units of a product per month at a price of $10 each, that tells us that, well, here, let me jump to the next slide to kind of help walk us through this. For those of y'all at home, what I'm looking at right now is slide 23 of week 6.2. I'm going to jump straight to the next slide because I thought it was going to help and it doesn't. All right, we're going to have to build this from the ground up. What we got is that a business sells 2,000 units of a product a month at a price of $10 each. And when it does, it can sell 250 more items per month for 25 cents a reduction in price. What price per unit will minimize the monthly revenue? So what we're trying to do is we're trying to come up first with a revenue function with respect to x. And instead of trying to cram this all through, let's jump to here. And I'm going to walk y'all through all of this. Okay. So the first thing we're going to do, we're going to let X represent the number of units sold in a month, and let P represent the price, and R represent the revenue. So we know the revenue is going to be X times the price. having said that, we know that the price, $10, is going to correspond to 2,000. And the price, $9.75, is going to correspond to the X value being 2,250. From this, we can set up the point slope formula. So what we've got is let me step back just a little bit more. We're going to find the point slope formula for price. We're told we've got P or X and P, right? Because the price formula is a function of X. It's equal to P. We've got the point X equal to 2,000 corresponding with price equal to 10, so 2,000 and 10. We have the other point two, 250 and 9.75. Now we're going to use these 2 points in point slope formula. We know that point slope formula is equal to y minus y1 equal to m times x minus x1, where m is equal to y2 minus y1 over x2 minus x1. So we can find m using these 2 points. M is going to come out to be 10 minus 9.75 divided by 2250 minus 2000.
What did you do the other one? 2000 minus.
From our x values. So I should point out this point xp, p is playing the role of y here, right? And x is going to keep playing the role of x. So what we're doing is we're using these 2 points to say, all right, with point slope formula, if p is our y value, then the difference from 10 and 975 divided by 2000, 2250, and I wrote that backwards. That's going to give us our m. This is going to come out to be 0.25 over negative 250, right? So we've got our m value now. Now we can set up point slope formula and solve for p as a function of x. Is everybody with me at home?
Yes.
Awesome. All right. So setting this up, we've got y minus, picking one of these. 10 is a nice round number, so let's use that. is equal to negative 0.25 divided by 250 times x minus the associated x value is 2000. Associated, I should say. This should be P. I apologize for that. Now from here, we're just going to solve for x. Solve for P. So we're going to add 10 to both sides and reduce everything as much as we can, right? So what we're going to get is that price as a function of x is equal to negative 0.0001 times, my mistake, 001 times x plus 12. Yes, I am cheating and looking at these notes as I go through. All right. So we just solved for this, right? Now, let's erase this and this. Put up our price function. P of x is equal to negative 0.001x plus 12. This tells us then that our revenue function is going to be equal to x times our price function, so negative 0.001x squared plus 12x, right? Wow, that wasn't even close to being straight. Now, going back to the original question, we want to know what price per unit will maximize the monthly revenue, right? So what are we saying here? What are we asking?
You have to find the derivative.
Yeah, we're going to have to do a couple of different things here, right? We're going to have to apply the derivative to our revenue function. That's going to give us the x value that corresponds with the maximum or minimum revenue, right? In this case, the maximum revenue. When we take the derivative, set it equal to 0, we're going to get that x is equal to 6,000. Doing that really quick. D dx r of x is equal to negative 0.002x plus 12. Setting this thing equal to 0. It's going to tell us that negative 0.002x plus 12 is equal to 0. So we can move to the other side and say 12 is equal to 0.002x. Divide both sides by 0.002x. We get that x is equal to 0.002 in our denominator, 12 in our numerator, or 6,000. So we're maximizing revenue. Now we need to go back to the price function and put in 6,000. When we do, well, let me write this first. So 6,000 units will maximize our revenue. Now we need to go back to our price function and plug in 6,000. It's going to come out to be $6. So let's go back and look at what this original question asked really quick. This original question gave us that a business sells 2,000 units of a product per month at a price of $10 each. And then it told us it can sell 250 more items for 25 cents less. That gave us those 2 points. That gave us the points X and P, 2,000, 10, and 2,250, 975. And we said, all right, using this, we can find a linear equation of our price with respect to X, right? Or for our price, I should say. So we have to use point slope form. So we have to go back and say P minus P1 is equal to M times X minus X1 where M is equal to the change in our price over the change in our demand. This then gave us an ability to solve for our price function, which then let us solve for our revenue function, which we then maximized using the derivative. Once we did that, we took that X value and put it into our price function to find out what the price should be set at to maximize our revenue. People at home, does this make sense?
Yeah.
Yeah? Awesome. So, for the sake of time, I'm going to jump to price elasticity. Price elasticity is a way of measuring the way demand and price relate to each other. It's a way of saying, all right, if demand increases like this, how will price have to increase accordingly, or vice versa? We represent it using eta. So we say eta is equal to P over X divided by the derivative of price over the derivative demand. Or my mistake. Not over the derivative of demand, but price differentiated with respect to demand is what I'm trying to say. Having said that, we say that demand is inelastic if the absolute value of eta is greater than 1. If eta, the absolute value of it, is equal to 1, we say that it's unit elasticity. And eta less than 1, demand is elastic. So just a couple quick points on how elasticity represents different behaviors within our price and demand. If demand is elastic, the decrease in price is accompanied by an increase in unit sales. Sufficient to increase the total revenue. And inelastic as well, gives us the other case. So what we're saying here is X representing demand, R representing revenue. We say that we're elastic in this case, right, where dr dx is greater than 0. We're inelastic where dr dx is greater than or is less than 0. And this would be unit elasticity, or my mistake, no, it's not the unit elasticity. This is the split between the two. Is everybody cool with this? I'm going to take the silence to be a yes. All right, so we've got our demand function, price as a function of X. And we're told that it is equal to 18 minus 1.5 times the square root of X. So the first thing we're going to want to do is calculate what eta is, right? Eta is our demand function divided by X. That quantity divided by the derivative of demand with respect to X. right? So why don't we do this in parts? Let's calculate what p divided by x is. And then let's calculate what the derivative of p with respect to x is. This is going to come out to be 18 over x minus 3 over 2 times x to the negative 1/2 power dp dx is going to come out to be, we're applying the power rule, right? So this is going to come out to be negative 3 over 4 x to the negative 1/2 power, right? Using this now, we know that eta must be over x minus 3 over 2 x to the negative 1/2 power. All of this divided by 3 over 4 x to the negative 1/2 power, right? So we can simplify all of this a little bit. Thank God, because that looks like a mess, right? We can simplify it to come out to be negative 24 square root of x over x plus 2, which we could simplify this more too, but let's leave it in this form. So now, what we want to do is find when this is unit elastic, inelastic, inelastic. And going back to the original problem, we're given that we're working on an interval x is between 0 and 144 closed. So we're using both of those values, 0 and 144. So what are we going to do here? How are we going to solve this?
We have to plug it into 0.
Yeah, well, sort of. What we've got to do here now is we've got to find when eta is equal to 1 in that interval. We've got to set the absolute value of this thing equal to 1. When we do, we're going to get that the absolute value of eta is equal to 1 when x is equal to 64. So this is going to break up our intervals now. Now we know to check from 0 to 64 and 64 to 144. So we take a value from here, we plug it in to see if it's inelastic or elastic. And we take a value from here to see if it's inelastic or elastic. Does this make sense to everybody at home?
Yes. So doing that,
we find that in this interval, we're going to be elastic, and in this interval, we're going to be inelastic. So pro tip, the easiest way to go about finding where your intervals of elasticity and inelasticity are is to look for where it's unit elastic, because that'll break up your interval even more. You'll know where to check. Because we're going to be elastic on an interval, but unit elastic on a value. So elasticity, inelasticity implies an interval. Unit elasticity implies a number. Check that number, you'll get your intervals out. Check those interval values, which ones belong to what. And from there, it was just asking us to interpret what that was telling us. Having said that, there is a nice little review page on slide 36. I would suggest everybody check it out. It just goes over business terms that we've used so far in Calc. It really just breaks out like what you're going to be looking for in different types of problems. Having said that, since we are at the end of this slide and class time, I'll let y'all go. If y'all have any questions, I'll stick around.